Well, hello there. Welcome back to another calculus video. So happy to be here with you today to talk about calculus, particularly the practice of implicit differentiation. It's just differentiation when I have an implicit function of a variable. Allow me to demonstrate. Suppose that I have an expression that binds together x and y, so that I have, say, like y squared x minus x y squared equals 5. And I know that no matter what x values and y values I take, this is nonsense, isn't it? I meant to go x squared y. There we go. Otherwise, I just had 0 equals 5. Okay, I caught myself on that one. Okay. So if I put in x and y values, I better get 5. And if I put in an x, you can find a y. Like, for example, if I'm like x equals 3, okay, then it would have y squared times 3 minus 9 times y equals 5. I don't know why I wrote 0 there. Just so used to writing equals 0 equals 5, which means that I then now have a quadratic equation in y. And so let's write that as 3y squared minus 9y minus 5. There's my equals 0. And then I can use the quadratic formula and find a couple of y values that correspond to that x value, right? So like I fed in an x, right? I told this. That was me right there. And then I can find a y. So given an x, we can solve for y. In this case, I get 2 different y values that are going to satisfy this. I'm not going to go the distance of actually finding them right now. I am going to go the distance of actually finding one right now. Let's go ahead and find it. So the point is that this is not a function, and then we're going to find the derivative of this thing at a particular point. Okay. So let's quadratic formula this thing. We're going to have 9 plus or minus the square root of 81 minus 4 times 3 times minus 5 all over 6. 4 times 3 is 12. That's 60. That's 9 plus and minus the square root of 81 and 60 is 81 and 60 is 141 all over 6. Okay. So given a y, I can find an x. No, wait. Given an x, I can find a y. Oh, given an x, I can find a y. Okay? So that means I'm not focused on this particular number right here. Given a y, given an x, I can find a y. Okay, so given x equals 3, I know that y equals 9 plus or minus the square root of 141 all over 6. Okay. Groovy. Okay, that means x was independent and y depended on x. Y depends on x. I feed in x's and I get y's. That means that y equals y of x, a function of x. In some sense, it's not a function strictly speaking because there were multiple y's that we get because this is some curve in space. I don't know what it does. I didn't look at it. Maybe it looks like that, right? Maybe it looks like that. And like that's the value 3 and that point right there were these 2 y values that we found. The point's not the particular shape of the curve. The point is that locally, if you just look at this region right here, it is just a function. And there is, my friends, a well-defined tangent line to that curve at that point. And I want to be able to find the slope of that tangent line to that point, even though the curve was given implicitly in this relationship, okay? So this right here, y is implicitly a function of x in this thing right here. And I want to find the slope of the tangent line to the curve at a point, and we're going to do it at the point 3 comma that. Probably won't deal with the plus minus. We'll choose a branch. Okay? So that is to say that I have a relationship like this, except y is a function of x. I'm going to note that in a different color so it doesn't get lost. Because one of the dangers of like this of x thing is that it looks like I'm maybe multiplying by x there, but I'm not. I'm just reminding myself, I'm just reminding us that y is a function of x. Okay. So let's focus on taking the derivative of this expression right here. So I have something equals something. This thing right here on the left-hand side always equals 5, which means that the rate of change of this expression right here is 0. Okay, another way of saying that, I'm just going to differentiate both sides of this equality. So I'm going to differentiate, and I want to apply the ddx operator, ddx of y squared x minus x squared y equals ddx of 5. Because if these two things are equal, then the rates of change have to be equal also. Okay. So we get to use the normal rules in terms of like the sum rule and the difference rule. All the normal rules are in effect here. So on the right-hand side, I have equals 0 because the derivative of 5 with respect to any variable is 0. On the left-hand side here, I need to take the derivative of each of these two expressions separately. I need to take the derivative of y squared x dx y squared x minus ddx of x squared y. I've got a product. So I'm going to start using, no, I'm not. I was thinking about using primes, but I'm not. So I'm going to apply the product rule to this thing here. So I'm going to have ddx of y squared times x plus y squared times dx of x minus, now I'm going to use the product rule on this expression right here. Careful of those parens. ddx x squared times y plus x squared times dx of y equals 0. Okay, before we start getting too lost here, our goal is to try to recover an expression for dy dx. Okay, because I want to find the slope of the tangent line to the curve at the point 3 comma 9 plus 140 square root of 141 over 6. Okay. And I'm going to do that by practicing implicit differentiation. I started with an equality. I'm going to differentiate both sides. On the right-hand side, I got derivative 0. On the left-hand side here, I have to just take derivatives of things. And I'm at the point now where I need to take the derivative of y squared. Okay? But y is a function of x. So, left-hand side, I still have 0. So here, I have the derivative of y squared is 2y, but I need that's supposed to be a y. 2y, and then the inside thing is y, which is a function of x, and I have to chain out the derivative, and I have dy dx times x plus y squared d dx of x is times 1 minus, where it's going to close, d dx of x squared is 2x. Here's my times y, plus x squared, d dx of y is dy dx. The whole thing is equal to 0. Okay. I'm going to erase my times 1 because that's not helpful to me right now. So I've got this expression equals 0. And I would like you to note, I've got a dy dx right here, and I've got a dy dx right here. And they always appear linearly. It's never going to be dy dx squared or something like that. It's always going to be dy dx. So I differentiated, and now I'm going to solve for dy dx. I'm going to solve for dy dx. So I think I better move up here in order to have enough room. I'm going to distribute this minus sign across each of those two quantities. Be so super careful with your parentheses when doing product rule and stuff like that. So what I'm going to try to do is I'm going to try to put everything that doesn't have a dy dx on one side and everything that does on the other. So how about I'm going to move this piece right here that I underlined and this piece right here. Those are going to be moved to the other side. Those are going to move to the other side of the equal sign. So, boop, they're going to go over there. So, instead of 0, now I'm going to have minus y squared, because I moved it to the other side, plus 2xy equals 2y dy dx. And then the other piece, I've got this minus sign, minus x squared times dy dx. And now I want to factor out my dy dx. I'm going to reorder these. I'm going to write that as 2xy minus y squared equals 2y minus x squared dy dx. So much algebra. And then finally, I'm going to divide by this to get dy dx by itself. Okay? So then I finally have 2xy minus y squared over 2y minus x squared equals dy dx. I think I'm questioning the symmetry in this. This feels a little off to me. I feel like we should go back and check that statement. Because I feel like it should be symmetric. Why is it not 2x minus y squared? Did I leave a y left over somewhere? I think it's okay. If you find an error, let me know. I think it's okay. Everything looks okay to me so far. Okay. So, this expression that I found tells me dy dx, or the slope of the tangent line, at some x, y. It doesn't tell me how I got x and y. It only says, given an x and y, how do I get the slope of the tangent line at that point? Is by this formula right here. So as a function of the coordinates on the curve, what is the slope of the tangent line? That is. Okay. So, returning back to where we started from, I have my original function, which is the relationship between x and y. I'm only considering points x and y that satisfy this relationship. If y squared times x minus x squared times y doesn't equal 5, then the points don't lie on the curve, and we're not going to be considering them as far as valid inputs here. If I wanted to, I could fix some value of x and then use algebraic techniques to solve for points y. That is to say that y is implicitly a function of x. Y is implicitly a function of x. And then I engage in the process of implicit differentiation, which I will summarize right now. Implicit differentiation is going to be like, yeah, given a point on my curve, I'm going to differentiate both sides of my equation. And we've got some notes here. Derivatives of y produce in the fashion of chaining out a dy dx, which we can write as y prime if we really want to. So you have to be careful. Anytime you take a derivative of an expression in terms of doing one of these things that has some y in it, boop, you get a multiplicative factor of dy dx, which is y prime. Okay. 2, we're going to solve for dy dx. And then 3, we haven't done this step yet. We're going to plug in your point. Okay. So we could then plug in one of these points. Let's say choose the plus branch of those two. We can get the slope of the tangent line at 3, 9 plus the square root of 141 over 6. Okay, so step 3 in this is we're going to plug in my point being 3, 9 plus root 141 over 6. So we're going to plug those in to this expression. 2 times 3 times 9 plus square root of 141 over 6 minus 9 plus the square root of 141 over 6 squared all over 2 times 9 plus the square root of 141 over 6 minus 9. And that's equal to my y prime value, the slope of the tangent line at that particular point. I'm not particularly interested in continuing on with my quest to simplify this expression. I'm going to call it good there. You should probably note that many of the examples that you will work with when doing this kind of stuff have been specially crafted so that you'd get nice answers when you do this. And so they'll often choose like 1s and 0s for these things, because you get really nice numbers when you choose 1s and 0s, and like anything else, you're going to tend to get like this, like, you know? So, and there's enough algebra going on that there is merit in trying to keep things simple in terms of evaluation with ones and zeros. Yeah, so that's the point of implicit differentiation. I wanted to say right now, or at least for finding slopes to curves that are given implicitly through relationships like this. Implicit differentiation does show up in other contexts as well, like related rates problems and functions of time, but we're going to save that for another time. So thank you very much. I appreciate you. Have a lovely day.